Hello, everyone. Today we have David Gouldin talking about import travel time, primer on time zones in Python. Please help me welcome him.
The on switch helps. How about now? Great, cool. Let's get started. All right, today I'm going to talk about a fascinating and potentially maddening topic, time zones. First, a quick show of hands. Who here has ever had a bug in production code as a result of time zones? Yeah, that's a lot of hands. Good. You're all in the right place. Time zone bugs have caused me many hours of pain, but the good news is that we can understand them and we can master their use in Python. Hopefully by the end of this talk, you'll understand how to properly use time zones in Python and where the sharp edges are. But before I can convince you that it's worth learning how to use time zones properly in Python, we have to agree that time zones are worth supporting in the first place, right? I like to say avoiding hard problems is better than solving hard problems, so why support time zones at all? I mean, after all my customers are in the US. It's not like I'm doing super complicated math on date times in my app. And if I find out later I really need time zone support, I can always go back and add it, right? Well, I have some bad news if any of those lines of reasoning sound like something you've heard or said before. There is no escape. For any application that deals with date times in any way, and yes, that's probably your application, you cannot escape the reality of time zones. And I don't know about you, but my laptop here is usually in Pacific time, well, Eastern time right now, and my EC2 instances in AWS are in UTC. So simply by developing on and deploying to different environments, I'm already having to consider time zones. And even if I only cared about one time zone, I still have to be aware of that time zone's rules to properly support it. And yes, it's possible to backport old code to properly support time zones. But as the voice of experience, let me tell you, it is much easier to add that support out of the gate. Okay, hopefully I've convinced you this is worth doing, but how hard can it be in practice? I mean, sure, there are a lot of time zones in the world, but keeping track of all that so I don't have to is what computers are good for. Besides, time zones are just a shorthand for telling you when the sun will rise and set somewhere. It's basically just the globe cut into 24 one-hour increments, which makes total sense. And okay, some places spring forward and fall back for some extra evening daylight, but all that stuff is planned out way ahead of time. It doesn't change that often. Oh, sure, but I mean, okay, at least I'm only ever going to be an hour off. So that's not so bad, right? Oh, boy. Okay, this is not going to be so easy, but it's doable, I promise. So who am I, and why do I care so much about time zones? Well, I used to be a developer like you, then I took an arrow.py in the knee. No, that's not right. No, I work at Clara Labs. All day, every day, I work on an application that schedules meetings for people. Not just that, but we schedule meetings over email, so all the time we're dealing with the ambiguities of human speech in relation to scheduling. I like to say that my work is at the intersection between email and calendars. It's a lot of fun. Not just that, but we're a human-in-the-loop system with people all over the world labeling our scheduling data, making decisions, and checking our work. So there's tons of potential for time zone bugs to sneak in. But at the end of the day, our customers really don't care about time zones and date time math. They just pay us to worry about all that calendaring stuff so they don't have to. So we've got to get it right every single time. All right, let's dive in. This is a primer, so we'll start at the beginning. What exactly is a time zone, and what is it comprised of? You can think of a time zone as a thing that takes a wall time and contextualizes it so that you can tell what moment in time it refers to. What does this mean? Well, if I say that lunch today, on May 11th, is at 1 p.m., I've told you the wall time of lunch. But without knowing the time zone is US Eastern, you would have no way of knowing when in time 1 p.m. today is. Now let's say I'm telling my coworkers back in San Francisco that my lunch is today at 1 p.m. If I didn't give them the context of a time zone, they couldn't know for sure that I actually meant 1 p.m. Eastern time, or if I meant like 1 p.m. in their Pacific time, is it 10 a.m., is it 1 p.m.? Again, it's only with the context of a time zone that we can know what moment in time is represented by a wall time. So I'm going to use the word wall time frequently during this talk. When I say wall time, I'm literally referring to the time a human in a given time zone would see on the clock on their wall. Well, technically it's a date time, so just picture a bunch of calendars underneath there. There are lots of time zones in the world, but the standard against which all other time zones are measured is Coordinated Universal Time, or UTC. UTC is generally what developers use when they want to identify a moment in time in a stable way. It has no daylight saving time, and its definition will never change. To continue to, I think slides are off, okay. To continue to stretch the string encoding analogy, think of it as UTF-8 for time zones. When you're not concerned with preserving a wall time, UTC is a safe bet. For all time zones not UTC, we need a set of rules to tell us how to resolve a given wall time to a moment in time. For that, there's the Internet Assigned Numbers Authority Time Zone Database, or OLSN database. This database tells us how far a given time zone is from UTC at a point in time. It includes daylight saving transition dates and any other offset shifts. These shifts can happen for all kinds of reasons. It also provides a unique string identifier, as well as an acceptable list of aliases for each time zone. The database is updated several times every year, every time a legislative body changes the definition of a time zone's rules. This is an example of an entry in the IANA database. It defines a zone's name, its base UTC offset, and a set of rules that modify that offset, in this case for daylight saving time. This is a fairly straightforward example, but some time zones can get pretty complex. If you care to dig into just how much work is involved in keeping time zone definitions current, you can download the set of files that make up the database and read the comments. Some of them can be really entertaining. For instance, we then double-checked by calling hotels and offices based in Tokelau. This is not something you want to maintain yourself. Be glad somebody else is doing this work for you. When you see all the information captured in a particular zone, it becomes apparent that a simple UTC offset on its own is an insufficient representation of a time zone. And since more than one time zone will share the same UTC offset at a given point in time, offset by itself doesn't imply a time zone. So while a date time with a UTC offset can give you a moment in time, you run the risk of ending up with an incorrect wall time for an intended time zone if you ever decide to modify it. All right, most time zones other than UTC have changed their UTC offset at some point. When that happens, you end up with one of two edge cases. The first is called an ambiguous time. Ambiguous times occur in the overlap between periods of different offsets with the same time zone. So, given just the time zone and its wall time, it's impossible to know which moment in time you're referring to, hence the name ambiguous. All ambiguous wall times occur at least twice. Don't ask about the more than twice case if you want to preserve your sanity. Ambiguous times most commonly occur when a time zone transitions off of daylight saving time. You can see in this diagram that when Pacific time falls back an hour, we end up with two 2 a.m. wall times, each representing a different point in time. The other edge case, when the UTC offset shifts forward and creates a gap in wall time, is called imaginary time. Imaginary wall times never actually occur, so they have no corresponding moment in time, hence the name imaginary. Imaginary times most commonly occur when a time zone transitions to daylight saving time. You can see in the diagram that when Pacific springs forward an hour, we end up with a gap in wall time between 2 and 3 a.m., for which there's no actual time. Many of the interesting failure cases in dealing with time zones happen because of how code deals with ambiguous or imaginary times. So keep these concepts in mind as we move into code examples later. So now that we've covered the basic of time zones, let's talk about support for time zones in the Python standard library. Python's base time zone class is called tzInfo. It's meant to be used as an abstract class, so you won't use it directly. Instead, you'll interact with it via subclasses whose instances define the behavior of specific time zones. The most basic job of a tzInfo subclass is to return the UTC offset as a time delta given a specific date time. The provided date time is treated as a wall time, so even if it has its own tzInfo property, that's ignored. Because time zones can exist either east or west of UTC, the value of the offset might be positive or negative. And since, as I mentioned before, a time zone's UTC offset can change due to things like daylight saving time, you should expect the return value can be different for different supplied date times. So here's an example of UTC offset for eastern side on either side of the daylight saving time transition. Notice that the Eastern Daylight Time offset is 1 hour later than the Eastern Standard Time. Daylight saving time is the most common reason for a change to a time zone's UTC offset, so Python gives it a special designation. The DST method returns the time delta representing the part of the UTC offset specifically due to daylight saving time. It's worth noting that UTC offset, the instance method, already takes DST into account, so you probably won't use the method directly in application code, the DST method app. We can take the same time zone and date times as the UTC offset example, and you can see that the 1 hour difference in offsets in either side of the DST transition border is because of daylight saving time. If you're using Python 3, and you really should be using Python 3 if you can, you get a handy-dandy tzinfo subclass built in called timezone. This subclass only deals with static UTC offset time zones, but if that's all you need, presumably because you're only dealing with timestamps and not wall times, then you're all set. It even includes a built-in instance for UTC itself, which can come in handy. There are 2 types of date times in Python, timezone-aware and timezone-naive. The difference is simply whether or not the timezone instance has a tzinfo property. Python's datetime constructor has an optional tzinfo keyword, which determines whether or not tzinfo is set on that datetime and determines whether it's aware or naive. It's also possible to ask Python to give you a datetime instance representing the current moment in time. By default, Python uses your system local clock to return a timezone-naive datetime, but this isn't particularly useful. Luckily, you can also pass a tzinfo instance into now and get a timezone-aware datetime in the time zone that you pass in. There's also a UTC now method, but if you really want UTC time specifically, you probably should be using a timezone-aware datetime anyway. So I recommend passing that UTC tzinfo that we talked about before into now instead of using UTC now directly. So you can see here that without passing a time zone to now, I get back my local Pacific time, and I get the same answer by passing timezone.utc to now as I do by calling UTC now directly, except that I get a timezone-aware datetime back calling now with a tz keyword argument. So if you have a timezone-naive datetime that you want to make timezone-aware, you can call replace on it and supply the tzinfo value, same as you would supply it if you were constructing a new datetime. It's important to note, however, that replace does not change the datetime's wall time, so if you do this, be sure that you intend for the timezone-naive datetime you start with to be the wall time for the resulting timezone-aware datetime. You can call replace on a timezone-aware datetime as well, which basically has the same effect. The wall time is kept, and the tzinfo is simply replaced with a new value. In this example, I'm replacing UTC with Eastern time, but the wall time is still midnight, January 1st, 2018. Notice the instance method returns a new instance and doesn't mutate the existing one. If you want to convert a timezone-aware datetime to a different time zone, you can call the asTimezone method with the time zone you want to convert to. Technically, you can use this method on a timezone-naive datetime or even without passing a tzinfo instance in, but it's probably not what you want to do, so I don't really recommend doing that. Like replace, asTimezone returns a new instance rather than mutating the old one. Unlike replace, asTimezone changes the wall time to reflect the difference in UTC offsets between the old and the new time zone for that wall time. Datetime has support for operators like addition and subtraction, but they're only supported when the datetime on both sides are either both naive or both aware. One surprising aspect of operating on timezone-aware datetimes is that the result can change depending on whether both datetimes are in the same time zone or different time zones. If the time zones are the same, Python operates on the wall time, the same as it would if you were operating on timezone-naive datetimes and then converting back to the timezone-aware datetime after. If the time zones are different, Python treats both datetimes like moments in time and simply operates on them the same as it would if they were both in UTC. So in this example, you can see that subtracting the same wall time with different time zones from each other returns the time delta representing the difference in those time zones UTC offset at that wall time. Python is treating both of these datetimes as moments in time, the same as it would if we were to convert the datetime on the left to UTC before subtracting. In the next statement, Python raises a type error because the time zone awareness of the datetimes doesn't match. But here, since both datetimes have the same time zone, DT2 ends up 30 days later than DT1 in wall time. Since DT2 is on the other side of a daylight saving time boundary, the difference between the two is actually slightly less than 30 days of real time. But that fact isn't obvious until we convert them to UTC and perform the same operation. So you can see the time deltas are different between DT2 minus DT1 and when we cast as time zone. This is tricky, so be really careful when you're working with time zone-aware datetimes to make sure you're performing the operation you intend to. So to handle ambiguous times, Python 3.6 introduced a new datetime property called fold. You remember when I said before that an ambiguous time can't represent a single moment in time with only its wall time and time zone? Well, now with fold it can. Python assumes there will be 2 moments in time associated with an ambiguous time. A full value of 0 represents the earlier of the two, and 1 represents the later of the two. Okay, so we reviewed the standard library's timezone support. You can see that on its own, Python has the potential for everything we need to properly handle time zones, but it leaves some assembly required on the part of the community to make working with time zones actually useful. Luckily, as is so often the case, the Python community has it covered. Let's talk about dateutil. Dateutil is a third-party library that the Python 3 docs recommend for dealing with time zones, and with good reason, as we'll get into later. It includes a utility method for getting a tzinfo instance given an IANA timezone name. And since those names uniquely identify a set of timezone rules, this is exactly what we want to do. It also has a UTC singleton in case you can't use the one provided by Python 3. And as you can see, the instances returned from getTZ are indeed tzinfo instances and adhere to its interface with things like a UTC offset instance method. Dateutil works really hard to get the details right around ambiguous and imaginary times too. In fact, it even provides a compatibility layer for the Python 3.6 fold property. Calling in fold from a version of Python prior to 3.6 will return a custom datetime subclass that includes fold property support. It's pretty useful. And if you want to know whether a given wall time is ambiguous in the context of a particular time zone, dateutil has a method for that too, datetime.ambiguous. So since we fall back when transitioning off of daylight saving time in US Eastern Time, wall times between 1 and 2 a.m. on November 4th, 2018 are ambiguous. The example here uses Python 3.5 to illustrate the custom datetime with fold subclasses fold support. And below, you can see that wall times within the ambiguous daylight saving time transition window of a time zone are determined to be ambiguous. Those outside the window are not. So 1:30 on the 4th, ambiguous true, 2:30, ambiguous false. Likewise, dateutil provides a method that tells you whether a given wall time is imaginary for a time zone. If you want to guarantee that you're always working with an actual datetime, you can use resolve imaginary. It will shift datetimes forward by the size of the imaginary window to give you a datetime that actually exists as a moment in time. Since we spring forward when transitioning to daylight saving time in US Eastern, wall times between 2 and 3 a.m. on March 11th, 2018 are imaginary. You can see here that wall times within the imaginary DST transition window of a time zone are indeed determined to be imaginary. 2:30 is not, does not exist, 3:30 does exist. And passing the same imaginary date time to resolve imaginary returns a date time shifted forward by 1 hour, the size of the DST transition. And if we pass a non-imaginary date time, we simply get the same value back. So passing in 2:30 gives us back 3:30. Passing in 3:30 gives us the same thing back. All right, that wraps up dateutil. Another widely used third-party library for dealing with time zones is PyTZ. This slide should look very familiar. Just like dateutil, PyTZ has a method for getting a tzinfo instance based on an IANA time zone name and includes a UTC singleton. And this code looks virtually identical to the corresponding dateutil slide. But don't let looks fool you. There are absolutely real differences in the tzinfo implementations of these two libraries. The most important thing to understand about PyTZ's tzinfo instances is that their UTC offset is static. Once you have an instance, any datetime you construct with that instance will have the same UTC offset. And potentially more surprising, the offset of the instance you get back from PyTZ's timezone method is the oldest one it has a record of. So if you've ever used PyTZ and seen some really funky offsets, this is probably why. All this makes sense and is fine when you understand the way PyTZ was intended to be used. You're never supposed to set a datetimes.tzinfo directly with PyTZ. Instead, you pass a naive datetime into the tzinfo's localize instance method, and it constructs a new tzinfo instance and returns the timezone-aware datetime with that tzinfo applied. So let's look at this in action. Constructing a datetime directly with a PyTZ tzinfo instance, bad. Look at that datetime. Its UTC offset is 4 hours and 56 minutes behind UTC. That is not what we want. Localizing the time zone using the tzinfo instance is good. We get an instance in Eastern Daylight Time with a 4-hour offset just like we'd expect. Another consequence of having static UTC offsets is that when you modify a datetime across a daylight saving time boundary, its UTC offset doesn't update, and so it's effectively wrong for that wall time. To solve this problem, PyTZ includes a normalize instance method. Pass it a timezone-aware datetime with a PyTZ tzinfo instance. That part's important. And if needed, it'll give you back a datetime with a corrected UTC offset. Normalize is idempotent and is a no-op if the UTC offset is already correct. So if you're using PyTZ, feel free to call it anytime you think you might need to. Again, provided that you're using PyTZ tzinfo instances. So let's look at normalize. In 2018, Eastern Daylight Time, again, ends at 2 a.m. on November 4th. So if we take midnight on the 4th and localize it, we'll see we're in DST. Again, because PyTZ tzinfos have a static UTC offset, simply adding a day results in a datetime that still has the DST offset, even though its wall time should be in standard time. It's only after we call normalize that we get an adjusted wall time with a proper UTC offset for that time zone. So why does PyTZ choose to do it this way? Well, it's because they were faced with the difficult task of supporting ambiguous times before there was any real support in Python for them. What they arrived at is a system that works even if it's a little clunky. You may have noticed that localize has a keyword isDST that I didn't really talk about. This is PyTZ's replacement for the fold attribute support. When the wall time you're localizing is ambiguous for a time zone, the value of isDST that you pass in determines which side of the fold you're on. If you want to know whether a time is ambiguous, you can call localize with isDST equals none, and it will raise an exception if it's an ambiguous time. So let's see this in action. Since we fall back, again, when transitioning off of DST in Eastern Time, wall times between 1 and 2 a.m. on November 4th, 2018 are ambiguous. You can see here that different values of isDST result in different UTC offsets, but the same wall time. This is how we can use PyTZ to disambiguate a moment in time from an ambiguous wall time. And as I said before, PyTZ will raise ambiguous time error if we specify none for isDST with an ambiguous time. Likewise, we can use normalize to shift an imaginary wall time to an actual moment in time. With PyTZ, we can actually choose the direction of the shift by choosing whether the imaginary time is localized in DST or not. And as with ambiguous times, we can detect an imaginary time by passing isDST equals none to localize. So again, since we spring forward with the transition to DST and Eastern Time, the wall times between 2 and 3 a.m. on March 11th, 2018 are imaginary. When we construct a non-DST imaginary time and normalize it, we get back an actual time shifted forward by an hour with a daylight time UTC offset. When we construct a DST imaginary date time and normalize it, we get back an actual time shifted backward an hour with a standard time UTC offset. And calling localize on an imaginary time with DST isDST equals none raises non-existent time error. So that covers working with time zones in both Python's standard library and third-party libraries. Let's move on to some strategies I found useful when developing applications. So I like to make an analogy to Unicode when thinking about time zone awareness. If you've never watched Ned's Unicode Sandwich talk, I would recommend that you definitely go watch that. It made things really clear for me when dealing with byte strings and Unicode strings. And I think there's a lot to be gained to applying the same idea of the Unicode sandwich that he introduces to datetimes in the form of a timezone-aware sandwich. It's very rare that you actually want a wall time with absolutely no context to the moment in time it represents. So I think it's best to push those time zone naive date times out as far to the edges of your application as you can and try to maximize the surface area where you're dealing with time zone aware datetime instances. And anytime you're dealing with a timestamp in your application, meaning you only care about the moment in time and you don't need to preserve the wall time, do yourself a favor and work directly in UTC. That way, you won't have to worry about the complexities of offset changes, and things like logging and inspecting local scope when debugging will always be consistent. This one is really important because it is so tempting to make assumptions about date times. If all you have is a date time and a UTC offset, you can tell its moment in time, but its wall time is effectively undefined. Refuse the temptation to guess its intended wall time or time zone. Thank the sender kindly, convert it to UTC, and move along. I wouldn't even preserve the offset because it's so tempting to try to infer some kind of meaning from it when it effectively has none. And keep your time zone database current. I've definitely been bitten by this before. It's so easy to lock your pip requirements to a specific version of one of these third-party libraries and just not think about it. But both PyTZ and dateutil release new versions every time the time zone database is updated, and that happens several times a year. So you want that new version. So be careful about how you lock your dependencies. But even if you follow all of this advice, at some point your application is probably going to have to communicate with some other process over some kind of transport protocol. So let's talk about dealing with date times at the edges of your application. When deciding about how to do things like serializing or persisting date times to a store, first you have to decide what you want to preserve. As I mentioned before, if all you want is the notion of a moment in time, just convert to UTC, then either indicate that you're using a 0 UTC offset, or even just document it, and that date times are all intended to be in UTC. If you're trying to preserve a wall time, it gets a little trickier. You'll need both the naive date time and an identifier for its time zone, preferably the IANA time zone name. With that in mind, let's talk about serialization. The most common datetime serialization format is ISO 8601, also called RFC 3339 for use on the internet. ISO 8601 can represent dates, times, date times with or without a UTC offset, among a few other things that are beyond the scope of this talk. Just a note, if you ever see an ISO 8601 string ending with a Z, that's shorthand for UTC. Conveniently, datetime has a built-in ISO format method that will produce valid ISO 8601, complete with UTC offset if the datetime is time zone aware. So great, that's solved for us. Dateutil makes deserializing ISO 8601 strings equally convenient by defining an ISO parse method in its parser module. The method generates a time zone aware datetime with a fixed UTC offset, fixed UTC tzinfo object if the string includes a UTC offset, and it even parses the Z shorthand for us. So you see Z and +0 results in the same tzinfo object, and -5 produces 1 with a fixed offset. Remember, refuse the temptation to guess what time zone the datetime is actually in. ISO 8601 is only useful for representing timestamps or moments in time. So what if we want to serialize a wall time? Well, it turns out that's not quite as straightforward. What we need out of the tzinfo instance on that datetime is its original time zone name. But dateutil doesn't yet keep that name around. There is an open issue for it. As a workaround here, I'm creating a wrapper around gettz that monkey patches the name onto the resulting tzinfo instance. And as long as I know that my datetime has one of those monkey patched instances, I can pull it back out and pair it with a time zone naive ISO 8601 representation of the datetime. So then I get this two-tuple with ISO 8601 on the left and the time zone name on the right. It's a bit of a hack, and it's not very generalizable, but it does yield a format that preserves wall time. The reverse operation is less problematic because, as we already covered, gettz will happily take an IANA name and convert it into a tzinfo instance. And so then when I combine the ISO parse and replace its tzinfo with the one we get from gettz, we end up with a datetime-aware datetime object, a timezone-aware datetime object, sorry. You might have noticed that nowhere in talking about serialization and deserialization have I mentioned strptime and strftime. Beside the fact that I find their format strings difficult to remember, their support for UTC offsets can be a little problematic. There was a point before Python 3.2 where you couldn't get back a datetime-aware datetime, but even today, if you're using ISO format, there's no way to parse its result back into a timezone-aware datetime. Though there is a from ISO format method coming in Python 3.7. Mostly though, I prefer dateutil's ISO parse because ISO 8601 allows for many variations, and I just trust them to get it right. But nobody serializes in a vacuum, so let's take a moment and talk about everyone's favorite complaint with regard to datetimes and serialization. That's right, it's JSON's lack of datetime support. JSON has no official support for encoding or decoding datetimes, so Python's default JSON encoder will fail if it encounters a datetime instance. But Python has an escape hatch in the form of custom encoder classes. By subclassing the default JSON encoder, we can use ISO format to serialize our timestamps, and then we pass our subclass into JSON dumps, and out pops our serialized ISO 8601 timestamp. Using that same get.tz wrapper hack I mentioned before, we can also create an encoder class that handles wall times. Here I'm returning a dictionary with separate keys for datetime and timezone just for explicitness. Of course, you may have a single JSON payload where you want to mix timestamps and wall times, in which case you'd have to do something a little more sophisticated, like creating subclasses of datetime to indicate the intent of that time, whether it's intended to be a wall time or intended to be a timestamp, and then is instance branch on which one it is to do the right thing. But we can handle both of these cases. Another edge your application is likely to encounter is persisting datetimes to a data store. There are all kinds of data stores out there, but let's just focus right now on a couple of the most common relational ones, Postgres and MySQL. Postgres has a couple of datetime types. Its default timestamp represents a timezone naive datetime. That's without timezone, which is implied. It's worth noting that Postgres will allow you to operate on this type with other timezone-aware datetimes. And in that case, Postgres assumes the timestamp represents a wall time in its local time zone. This can yield surprising results, so I just don't recommend that you do it at all. And while your client library is likely to do the type format preparation for you, know that ISO 8601 strings are acceptable as input in Postgres. So when we create a table with a timestamp column and insert a row into that table, we get back basically what we put in. Its ISO format is slightly different than the one that I used, but it's the same information. Postgres also provides a version of that timestamp data type that includes support for storing UTC offsets. It will accept timezone data in the form of a direct offset, a short name, or a full IANA timezone name. But these are only used by Postgres to convert the timestamp into UTC for storage. When you retrieve a timestamp with timezone column, Postgres converts it into the UTC offset of its local time for display purposes. This is just a convenience. Postgres has no first-class timezone type, so the datetime fields by themselves are really only useful for preserving timestamps, not wall times. So you can see that while Postgres will happily accept our full timezone name as input, what we get back is a simple ISO 8601 string with the UTC offset of its local time zone. When we change the local time zone, we get the same moment in time, just with a different UTC offset. As I mentioned before, when developing Python applications, your client library should take care of most of this for you. So here you can see PsychoPG2, which is a popular Postgres client library, understands how to prepare datetime instances as arguments of Postgres queries and how to turn fetch Postgres timestamps back into Python datetime instances. Notice that PsychoPG2 is creating its own tzinfo subclasses with a fixed UTC offset when we're using timestamp with timezone. Just like Postgres, MySQL has a timezone naive date type. Again, ISO 8601 works just fine as an input format, but it's important to know that if you get too funky in your formatting, MySQL has a mode where it will store all zeros instead of failing loudly. It'll just issue a warning, so be careful with that if you're using MySQL. This should all look pretty familiar. It's nearly identical to the earlier Postgres example, just with a different type name. So what we put in, we get back out. MySQL does include a data type that's intended to be timezone aware for some definition of aware. The timestamp type accepts data in the same timezone naive format as its datetime type, but it assumes that the UTC offset that you're sending with it is the same as the session's current time zone. MySQL will use that implied UTC offset to convert the datetime to UTC for storage. When the timestamp is retrieved, MySQL will again use the session's time zone to convert the stored UTC timestamp into its local time, but the value looks like a time zone naive datetime still. What this means is that if the session used to store the timestamp and the one used to retrieve it have different time zones, the retrieved datetime will be different than the stored one with no explicit UTC offset to indicate that what you're retrieving isn't what you stored. So you can see here that I'm setting the session's time zone to UTC and then storing a datetime that looks like it's time zone naive, but it actually is intended to be aware with the UTC offset equal to the session's time zone, which in this case is 0. As long as the same time zone is set at query time, everything looks okay. So you can assume that that datetime that comes out is in UTC. But if I use a session with a different time zone, I get a different datetime back. This is fine, really. I suppose your client could be smart enough to inspect and store the session time zone in order to do the right thing on the way in and out of the database, but that also assumes nobody else is using your database or that they're not going to mess it up themselves. It's a pretty big foot gun in my opinion, so I would just avoid timestamping MySQL completely. For storing wall times, the same rules apply as serializing them. You want to split them up into 2 columns, one for the time zone naive datetime and the other for the time zone name. If your Python client or ORM of choice doesn't already support combining these 2 columns into a single timezone-aware Python datetime instance, you'll have to write that bit by yourself, but it's the safest way to ensure that the wall time you intend is preserved. For timestamp storage, Postgres' timestamp with timezone does a good job preserving the moment in time. And as I said before, when using MySQL, just avoid timestamp and store naive datetimes converted to UTC so you don't get surprised by its implicit handling of UTC offsets. And if your code needs to work with multiple data stores, the lowest common denominator is the MySQL approach, storing timezone naive datetimes in UTC. That puts the onus on your code to correctly convert them to timezone-aware datetime instances, but at least you can guarantee consistent behavior between stores. All right, hopefully by this point, you feel pretty confident in your understanding of time zones and how to deal with them in Python applications. So in case you're like me and have a max attention span of about 10 minutes, I wanted to reiterate these overarching points. Even if you're only dealing with one locale, time zones matter. You have to think about them. Using a timezone-aware sandwich in your application will prevent bugs, so push those timezone naive datetimes out to the edges when you can. And always, always be aware of whether your data is intended to be a timestamp, which is a moment in time, or a wall time. Last but not least, you can do this. It is possible. I believe in you. I wanted to give a special shout out to Paul Gansel. Paul, you here? Want to wave? All right, there's Paul. Datetime util maintainer who has graciously offered his time to help me with this talk. The moment he heard I was talking about time zones, he emailed me and said, hey, I want to help. And he was a huge resource in me preparing this talk. You should go watch his PyBay talk. You should read his blog posts. They're great. And feel free to come chat with me while I'm here, or if you want, you can reach me by email or on Twitter at any time. So that's all I've got. If you have any questions, you can step up to the mic right here. Thank you. Yes. Sure.
One other way you can serialize a time other than ISO format is the Unix datetime.
Epoch seconds.
Yes.
Yeah.
What does that look like? Is that a wall time? Is that a timestamp?
It's a
Is
timestamp.
it universal?
Yeah. So it's effectively the same as UTC. It tells you exactly what moment in time because everyone agrees on what the epoch is, but it can't give you any information about what date or what time of day it intends.
Perfect. Thanks.
Hi. In one of your slides, you briefly brought up Arrow. I was wondering if you could briefly go into what you think about that library versus some of the others.
I've used it only briefly. It was mainly just a joke because it fit in the meme. It's a bit like higher level, right? It's intending to be a convenient wrapper for doing operations. I don't have any strong opinions on it one way or another, really. I haven't used it enough to tell. But it seems fine. I don't have a very informed opinion, sorry.